Pharmaceutical manufacture involves two groups of staff: production staff and quality control staff. Production staff carry out the manufacturing process, taking raw materials and using them to prepare a bulk product, which is then packed into suitable containers and labelled. The process may include sterilisation. Quality control staff are involved with testing raw materials, packaging materials and products to determine whether they comply with required standards. Both chemical and microbiological testing are undertaken. The quality control pharmacist, however, is concerned with much more than simply providing an analytical service. He must be able to discuss any production problem which may arise, and he is involved in monitoring the manufacturing unit in various ways. It is necessary to ensure that pharmaceutical products are consistently made to the standard required. The procedures carried out in both the production unit and the quality control laboratory to achieve this are called good manufacturing practice, or GMP for short. Another term that is frequently encountered is quality assurance. Quality assurance covers every step that is taken to ensure that a product of a suitable quality is consistently manufactured. Quality assurance is equal to good manufacturing practice plus certain other factors. A very important one being the original design and development of the product. Let us now consider the steps leading to a satisfactory product from the point of view of the quality controller, beginning with the important stage of formulation. Remain suspended whilst the dose is withdrawn. Here is a much better preparation. This product is subject to oxidation. This formulation has had an antioxidant added to it. Here is a product which does not contain an adequate antimicrobial preservative system and has become contaminated during use. Clearly, a variety of factors must be taken into account when new products are being developed, and the production unit will need to prepare trial batches so that chemical and microbiological stability studies can be carried out by the quality control section. Once a satisfactory formulation has been achieved, a master batch sheet is prepared by the production section and approved by quality control. Photocopies are used as batch sheets for individual batches. An adequate supply of raw materials is obviously necessary for production. Standards for raw materials are found in the British Pharmacopoeia or British Pharmaceutical Codex. These standards are usually adopted without modification, although not every official test will be carried out on every batch. Where there is no official monograph on a raw material, a set of standards must be drawn up. The first step in testing a raw material is to check that its appearance is satisfactory. Sometimes raw materials may be rejected on appearance alone. Here, for example, are some chloral hydrate crystals, which are pale yellow instead of colourless. Next, it is necessary to carry out tests for identity. Labelling errors are rare, but they do occur, and they can only be detected by testing every container. One example that has been reported was acetic acid labelled as hydrogen peroxide. Identity tests may involve simple chemical tests, or the determination of a variety of physical constants, such as melting point, weight per mil, or refractive index. The determination of the infrared spectrum is often used for organic compounds. Physical constants, as well as being used in identity testing, are useful indicators of purity. For example, the melting point of an organic compound is usually depressed appreciably by a small quantity or even traces of an impurity. Determination of the weight per mil and refractive index is carried out for many liquids. These include fixed oils, such as olive oil and arachis oil, and chemicals such as glycerol, as well as some solutions such as syrup. Where possible, a quantitative assay is carried out on the raw material. This may take the form of a titration or determination of the ultraviolet light absorption or some other suitable method. However, a material which gives a satisfactory assay result may still contain a variety of impurities in small or trace quantities, and it is usually necessary to set limits on some of these impurities and to carry out tests for them. Let's summarize what we have said about raw materials. A set of standards is drawn up. This includes a description of the substance, tests for identity, carried out on every container. The tests may be chemical or determination of physical constants. Determination of physical constants as indicators of purity. Quantitative assay, limit tests for small amounts of impurities. Having set the standards, it is necessary to ensure that all raw materials are in fact tested and approved by quality control before they are used in manufacture. Raw materials are therefore placed in a special bond store on arrival to await sampling and testing. All raw materials which are found to be satisfactory are labelled with a release label, which is signed by a quality control pharmacist. This label shows date released, expiry date, quality control code number. It is the quality control code number which is quoted on the manufacturing batch sheets and not the manufacturer's number. It is essential that all containers of raw materials used in manufacture carry a quality control release label, since this provides the assurance that the raw materials are suitable for use. Any batch of finished products which has been manufactured from untested raw materials would not be approved for use. Certain raw materials are relatively stable in well-filled, sealed containers, but may deteriorate once the container has been opened. Volatile oils are a good example of this. For such materials, the expiry date may take the form of a specified length of time after opening. In such cases, the container will have an additional label, and it is essential that the date of opening is entered on this, so that any remaining material can be discarded after the specified time. Once the raw material has been released, it is essential to ensure that the quality of the material is maintained. The storage conditions must be suitable, and a proper system of stock control and rotation must be employed so that old stock does not accumulate, for example, at the back of shelves. In some cases, a commercial pharmaceutical product may be used as an ingredient in hospital manufacture. For example, the material from capsules may be used to prepare a suspension, or a solution may be used to produce a more dilute preparation which is not available commercially. In such cases, the commercial product is treated in the same way as a raw material. You may think that because these products have been subject to the manufacturer's controls, there would be no need to retest. Mistakes do, however, occasionally occur, and sometimes goods are not up to a satisfactory standard. Look at the variety in these tablets, all taken from the same container. And here is a cream which is clearly unfit for use. These faults, of course, are visible, but some may not be. One very special raw material which is generated in the production unit itself is distilled water. This may be collected for use directly from the still, or it may pass to a storage tank, which in turn may be part of a ring main system. Samples of distilled water are tested at regular intervals in the quality control laboratory, both for chemical impurities and for the presence of microorganisms. Our next consideration is the manufacturing process. This is carried out in accordance with documentation, which has been approved by the quality controller. The rooms in which manufacture is carried out must be in a good state of repair and decoration, and must provide an environment of the appropriate standard. Environments are divided into 4 classes, in British Standard 5295, according to the number of airborne particles of various size. Aseptic rooms must meet the standard of the highest class of environment, Class 1. Rooms in which heat sterilised products are prepared and filled must meet the standard for Class 2. These classes are based on the room in an unmanned state. Both classes of rooms should have a minimum of 20 air exchanges per hour. Laminar flow cabinets are used to give a local Class 1 environment where required. The requirements for non-sterile manufacture rooms are of course less stringent. The determination of the number of air changes per hour is carried out at regular intervals by quality control staff. The air velocity at the inlet vents is determined using an anemometer or other suitable airflow meter, and the air change is calculated from the known volume of the room. Monitoring of the class of air entering the room and the general environment in the room itself is also carried out using an air particle counter. Similar determinations are carried out on laminar airflow cabinets. In these cases, it is necessary to pay particular attention to the seals around the filter, where considerable leakages can occur. Testing is carried out both at regular intervals and when filters are replaced. The purpose of supplying manufacturing rooms with filtered air is to reduce the levels of both particulate matter and microorganisms. Levels of microbial contamination are monitored by the use of settle plates, which are exposed for a specific length of time in designated positions. The plates are numbered according to position and returned to quality control for incubation and examination. Normally, settle plating is carried out on a weekly basis, although the day and time may be varied. Plates are also exposed each time aseptic manufacturing is carried out. Expected contamination levels vary from one location to another, and levels which are acceptable in a preparation room, for example, may not be satisfactory for a laminar airflow cabinet. It is usual to monitor a particular unit for a number of weeks before deciding what level of contamination may be accepted in each position. Levels of microbial contamination are also monitored with a suitable air sampler, which draws in a known volume of air and causes any microorganisms present to impinge onto an agar strip. The strip is then incubated and examined for colonies. This method has the advantage that some indication is obtained of the actual number of airborne microorganisms in a given volume of air. The contamination of surfaces may also be checked by using contact slides. In addition to monitoring the standard of the manufacturing environment, it is necessary for certain operations to monitor operator technique. This is particularly so for aseptic work. Consequently, during the period of induction and training, and at specified intervals afterwards, staff are required to carry out broth transfer trials. These involve transferring sterile nutrient broth aseptically between containers, after which the broth is incubated in order to detect any contamination. It is essential that operators be able to carry out these tests successfully. In the course of batch manufacture, a bulk product is obtained. Sometimes tests are carried out on the bulk product before packing, for example to check the concentration of active ingredient or whether mixing has been thorough. However, this is more commonly carried out in industry where much larger batch sizes are involved. Once the product has been prepared in bulk, it is necessary to pack it into the final containers. The type of container to be used will be specified on the batch sheet and must be suitable for the type of product being made. Amber glass may be necessary for light sensitive products, dropper bottles for eye drops, jars or tubes for creams, and so on. It is necessary to set standards for packaging materials in the same way as it is for raw materials. For bottles, the material is specified together with the dimensions and the allowable variations. This is particularly important in the case of glass bottles, used in the manufacture of heat sterilized products. The dimensions of the neck are especially important because of the necessity to achieve a good seal. Standards are also set for closures. Packaging materials include the labels that are to be applied to the final containers. Labels are treated in the same way as raw materials, being placed in bond on arrival until approved by quality control. Labels are checked for such things as spelling, legibility, and layout. Where a product is to be sterilized by heat in its final containers, it is desirable that the level of microbial contamination before autoclaving should be as low as possible. This is monitored by carrying out microbial counts on containers of the final product, which have not been autoclaved. Earlier steps in the process will also be investigated, and potential sources of contamination include the vessels used in mixing, the bottle washer and the bung washer, as well as the distilled water supply. The quality control pharmacist is involved in monitoring the autoclaves and hot air sterilizers which are used in the manufacturing unit. The quality controller must satisfy himself that the necessary level of testing is being carried out on the autoclave, that regular weekly maintenance is taking place, and that records are being properly maintained. Once a batch of a finished product has been prepared and labelled, it is placed into bond to await testing and release by quality control. Samples for testing of finished products are chosen at random by a member of the quality control staff, who will also examine the batch as a whole. In some cases, specific bottles are designated as samples, such as the first, middle, and the last bottle filled, and these are marked by the production staff. In the quality control lab, the general appearance of the sample will be examined together with the labelling. Testing will be carried out to confirm the identity of the product, together with an assay to determine the content of active ingredients. Other tests may be carried out if appropriate, such as pH determination, or tests for degradation products. Here are some examples of unsatisfactory products. This coal tar ointment contains many black specks. It has not been rubbed down satisfactorily. These ampules of zinc sulfate injection gave widely variable assay results, indicating inadequate mixing. This sample of chlorhexidine solution is being assayed by measuring the absorbance of ultraviolet light. The absorbance reading is above the upper limit of 0.497, indicating that the solution is too strong. Here is another example of chlorhexidine preparation that is coloured red, and some of the dye has precipitated. In addition to chemical testing, it will be also necessary to carry out a sterility test on sterile products. The preferred method which is being used here is to filter the entire contents of the containers through membrane filters with a maximum pore size of 0.45 microns. Any microorganisms present will be retained by the filters. It is necessary to divide the sample between two filtration units so that two different growth media can be used in order to test for both aerobic and anaerobic organisms. When the filtration of the sample is complete, the outlet below the filter is capped and the growth media pumped into each of the chambers in turn. The chambers are then sealed and incubated for 7 days. Any microorganisms retained by the filter will multiply, causing the medium to turn cloudy. Where membrane filtration is not possible because of the nature of the sample, the alternative method is to inoculate media with aliquots of the sample and incubate for 14 days. It is important to realize the limitations of sterility testing. A satisfactory sterility test does not prove that a batch is sterile, or even that the samples taken from it are sterile. What it shows is that the samples did not give rise to microbial growth under the conditions of the test. In the case of heat sterilized products, the most important evidence is the temperature record chart produced by the autoclave. This will indicate whether the batch has gone through a satisfactory sterilizing cycle, although, once again, it will not prove that the contents of each container are sterile. With aseptically prepared batches, the assurance given by a temperature record chart is lacking. Bubble point testing is carried out at the end of the process to check the integrity of the sterilizing filter used. But the whole process is much more dependent on operator technique. The chance of an odd container being contaminated is much higher than with heat sterilized products. Consequently, it is necessary to monitor operator technique using broth transfer trials to give an additional degree of assurance. Because of the length of time required for incubation in the sterility test, sterile products will need to be held in bond for at least 1 and sometimes 2 weeks. They must therefore be made well in advance of being needed. Once all the necessary tests have been carried out on a batch of finished product, a decision can be made as to whether it can be released for use. The quality control pharmacist reviews not only the testing results, but also the batch sheet and any other documentary evidence such as temperature record charts. If the product is satisfactory, the batch sheet is signed and dated, and release is effected by a member of the quality control staff. No batch, part batch, or container may be removed from bond without the authorization of a quality control pharmacist. Together, production and quality control staff work to ensure that only products of a suitable quality reach the patient. The purpose of quality control is to take an independent view of the production process and to carry out such tests as are necessary in monitoring it. The final responsibility for the release of a batch rests with the quality controller. Remember that quality control only acts as a safeguard to prevent the occasional faulty batch from being used. The quality of the product depends upon the care and skill of the production team and the environment in which it works. Quality must be built into a batch of product. It cannot be introduced at the end of the process by carrying out tests. It is a legal requirement of the Medicines Act 1968 that such a system of quality control should exist, and much detailed guidance on manufacturing and quality control is given in the Guide to Good Pharmaceutical Manufacturing Practice, commonly known as the Orange Guide. So what has this program been saying about quality control? There are 8 steps which should produce a satisfactory product. A satisfactory formula from which trial batches are made and on which chemical and microbiological testing takes place. Formulations and method of manufacture must be documented on a master batch sheet. All master batch sheets and general procedure sheets must be approved by quality control. Environmental checks are carried out regularly to ensure that the manufacturing unit is of a suitable standard. Equipment must be adequately maintained. Staff must be properly trained in manufacturing techniques and use of equipment. Techniques in aseptic work must be monitored by broth transfer trials. Raw materials must have been tested and approved by quality control. Tests may be carried out on the bulk product before packing, and procedures such as bottle washing and bun washing may be monitored microbiologically. The finished product is placed into bond to await testing and released by quality control. Provided that all these steps are taken, we can be assured that we have done everything possible to ensure that the products being made are of suitably high quality for use in patient care. Of the raw material to the material of the vessels or spatulas used. Measuring by volume should be carried out in calibrated vessels. Select the measure carefully, choosing one with a volume 2 or just above that of the amount required. Correct measurement is to the bottom of the meniscus. Small volumes, that is less than 5 mils, should be measured in a pipette. A pipette filler should always be used. Mixing should be thorough to ensure a homogeneous product. It is normally sufficient to mix simple solutions manually with a stirring rod. With more complex solutions or suspensions, mechanical mixing is required. This is an example of a mechanical mixer. It has various interchangeable heads for different applications. It is advisable to use mechanical mixing for any quantity around 5 litres or more to ensure a uniform product. A filling head is used to pack suspensions to make sure that the solid components remain evenly distributed. Other mixing heads are available which cause a shearing action and are used for forming emulsions. Mixing of semi-solids, that is, creams and ointments, can be carried out, if on a small scale, by using a slab and a spatula. If a powder needs to be mixed into a cream base, first obtain a smooth paste by adding a small amount of diluent to the powder. It's sometimes necessary to dissolve the powder in a solvent. Continue adding the diluent, a little at a time, mixing thoroughly with a spatula until sufficient diluent has been incorporated to make it possible to handle the mixture with a mechanical mixer, at which time the rest of the diluent can be added. The type of mixer used in this case would be one which uses a paddle-type mixing action. A further process called milling may be necessary to obtain a smooth, homogeneous product. The product is forced between 2 abrasive stones, one stationary, one rotating, the gap between them being adjustable. The particle size of the solids is reduced, thus achieving a better dispersal throughout the product. This process may be used for preparations containing substances such as ditronol or coal tar. Sterile production is more critical than non-sterile in that the final product must have no microbiological contamination and a minimum of particulate contamination. To achieve this, the environment in which preparation is carried out has to be very carefully controlled. Laminar airflow cabinets should be swabbed out before use with a bactericidal solution to minimize contamination, and they should be also switched on at least half an hour before work is begun. The quality of air is very important, and a regular change of filter is necessary in the laminar airflow cabinet to prevent clogging. Filters on the plant supplying air to the special production unit will also require changing regularly, so that the number of air changes is kept above the required minimum and the correct positive pressure is achieved. Aseptic technique is used when the final product cannot be heat sterilized. Solutions are made as far as possible from sterile components and are sterilized by filtration before being packed into pre-sterilized containers. There are several points to observe when carrying out an aseptic procedure. The correct changing procedure must be carried out. The cabinet swabbed down before use and turned on half an hour beforehand. Preparation is carried out well inside the cabinet and not at the front edge. The component should be sprayed with 70% industrial methylated spirit or other bactericidal solutions before being placed in the cabinet and their outer wrappings removed only just before use. The operator should avoid touching those parts of the equipment that will come in contact with the sterile components, that is, the ends of needles, quills, injection ports, and other similar key areas. The container should be sealed as soon as possible after filling. There are several types of filling machines for sterile products. They range from a filling capacity of less than 1 ml to up to 1,000 ml. Selection is made on the basis of the volume to be packed. For small quantities, a repeat dose syringe may be used. This syringe has a one-way valve through which the solution is drawn from the reservoir into the syringe barrel. When the plunger is pressed, the measured volume is expelled via the tip of the syringe. For large volumes, a peristaltic pump may be used. Fluid is pumped through a flexible tube by a roller device. The volume delivered is determined by a control which varies the time the delivery gate is open. For large volumes, other machines are available which can deliver volumes up to 1 litre. Filtering, connected closely with the filling process, is the filtration of the product. Filtration is sometimes used as a method of sterilization, but it is also used to remove particles from products that are to be sterilized by heat. There are various types of filters, including sintered glass and ceramic. The type most commonly used in sterile production is a membrane filter. Membrane filters are made from cellulose, cellulose esters, and other polymers, all of which do not shed particles. Their structure is uniform and in close-up resembles a honeycomb. These honeycomb-shaped pores interconnect and allow the passage of liquid whilst retaining particles. Different grades of filter have pore sizes varying from 12 to 0.05 microns. For sterilization, a pore size of 0.22 microns or below is necessary. Membrane filters are presented in disc or cartridge types. The advantage of a cartridge type is that there is a large filtering surface in a smaller package. The type of filter chosen depends on several factors: the viscosity of the fluid, the extent of contamination in the fluid, the degree of filtration required, the volume to be filtered. Large filters may need to have supportive frames, which also allow for the use of attachments. Small filters can be purchased as a pre-sterilized unit, ready to connect with syringes or tubing. Some products are terminally sterilized by heating. Usually an autoclave or a hot air sterilizer is used. Autoclaves range from small ones, suitable for eye drop bottles and ampules, to large ones like this, for bigger containers. Heat sterilizers are the subject of a document, HTM10, which governs their commissioning, maintenance, and use. The principles of sterilization are explained more fully in the program entitled Sterilization. Viewing of injectables for particles is an important stage in the manufacturing process. Preparations for injection should not contain any particle visible to the naked eye when viewed under polarized light. Any containers in which particles can be seen are rejected. Less critical, but still important, is the viewing of ophthalmic drops or sterile topical fluids. It is also desirable that non-sterile products, such as ointments, creams, or mouthwashes, should not contain any discernible particles or foreign bodies. Any that are unacceptable should be rejected. The final procedure in the manufacturing process is labeling. Each container is labeled with the labels issued for that product, which should show batch number and expiry date in accordance with the master worksheet. An example of the labels used should be attached to the batch sheet. A specific number of labels is issued, and these must all be accounted for at the end of the process. This is known as label reconciliation. At the end of the manufacturing process, an authorized member of the production staff checks the batch documentation and has a final look at the batch. The product is then placed into bond storage so that quality control sampling can be carried out, and subsequently microbiological and chemical testing to ensure that the product reaches the patient meeting all the required specifications.